Friends, today we will discuss the second lecture of infrared spectroscopy. Now we are going to the topics. How to know the number of fundamental vibrations. Fundamental vibration means transition from ground state to the first vibrational state level, energy level. For polyatomic molecules, the polyatomic molecules may have large number of fundamental vibrations. The number of fundamental vibrations is directly related to the degrees of freedom. In polyatomic molecules, no atom loses its degrees of freedom. Hence, total number of degrees of freedom in a polyatomic molecules means total number of degrees of freedom of all atoms within the molecules. The number of degrees of freedom of any atom means the total number of coordinates required to locate the atom in a space. It is well known fact to us that three coordinates, that is x, y, and z, are necessary to specify an atom in the space. So any atom in a molecule has 3 degrees of freedom. Thus, for a polyatomic molecule having n number of atoms, the total number of degrees of freedom is equal to 3n. When atoms combine to form molecule, there is no loss in the total number of degrees of freedom, but sum of translational motions are converted to rotational and vibrational motion. Thus, for the molecules having n number of atoms, 3n is equal to translational plus rotational plus vibrational degrees of freedom, or vibrational degrees of freedom is equal to 3n minus rotational plus translational degrees of freedom. When the molecule as a whole moves its motion, which is translational, can be described in terms of motion of its center of gravity, and it requires only 3 coordinates. Hence, out of 3n degrees of freedom, only 3 are translational for the molecule. However, the number of rotational degrees of freedom depends upon the nature of the molecule. The molecule may be linear or non-linear. When the molecules are linear in nature, its number of degrees of freedom is equal to 2. But why? The rotation along the axis of linearity, that is internuclear axis, produces non-effective change in rotational level. Hence, the total number of fundamental vibrations for linear molecule is equal to 3n minus 2 minus 3, that is 3n minus 5. But when the molecule is non-linear in nature, the molecule is free to undergo rotational motion along the three coordinates, and so the number of rotational degrees of freedom is 3. Therefore, the total number of fundamental vibrations for the non-linear molecule is 3n minus 3 minus 3 is equal to 3n minus 6. There's 3n minus 5 or 3n minus 6 vibrational modes are also called normal modes of vibrations. Out of these, there are n minus 1 stretching and rest are bending of deformation modes. For the linear molecule, we can calculate the degrees of freedom and the number of vibrational fundamental vibrations, number of stretching and number of bending. But in this way, from the chart, we can easily calculate this number. First of all, we are taking carbon dioxide. Here, the number of atoms is equal to 3. 1, 2, 3. So, the translational degrees of freedom is equal to 3. And as it is linear molecule, so the rotational degree of freedom is equal to 2. So, vibrational fundamental vibration is equal to 3 into 3, this 3, 3n minus 5, 3n minus 5. So, is equal to 4. That is total number of fundamental vibrations is equal to 4. Among them, n minus 1, that is 3, n is equal to 3, 3 minus 1 is equal to 2. 2 are stretching and bending is equal to this 4 minus 2 is equal to 2. For HCl molecule, here the number of atoms in the molecule is equal to 3, hydrogen and chlorine. Translational degrees of freedom 3 and rotational degrees of freedom 2, as it is linear in nature. So the vibrational fundamental vibrations is equal to 3 into 2, n is equal to 2 minus 5 is equal to 4. Among them, n minus 1, that is 2 minus 1 is equal to 1. 1 is stretching and this 4 minus 1 is equal to 3. 3 are bending in nature. For acetylene molecule, number of atoms is equal to 4. Here translational 3, rotational 2. So the fundamental vibration is equal to 3 into 4 minus 5 is equal to 7. Among them, stretching will be n minus 1, that is this 4 minus 1, that is 3. And bending will be 7 minus 3 is equal to 4. For this molecule HCl, n is equal to 1, 2, 3, that is n is equal to 3. Translational 3, rotational 2, and the fundamental vibrations 3 into this 3 minus 5 is equal to 4. Among them, the number of stretching will be n minus 1, that is 3 minus 1, 2, and the bending will be this 4 minus 2 is equal to 2. Now for non-linear molecules, the fundamental vibrations will be 3n minus 6. From where how we can calculate? For the benzene molecules, here the total number of atoms is n is equal to 12. We know that for the linear molecules, non-linear molecules, translational 3 and rotational degrees of freedom is equal to 3. So the fundamental vibrations will be 3 into n. N means 12. 3 into 12 minus 6. 3n minus 6. So is equal to 30. Among them, stretching will be n minus 1. That is 12 minus 1. 11. And rest as bending. That is 30 minus 11 is equal to 19. So the number of bending will be 19. For the water molecule, n is equal to 3. We know for non-linear molecule, number of translational degrees of freedom is equal to 3, rotational 3, fundamental vibration will be 3 into 3 minus 6, that is 3. Among them, stretching will be 3 minus 1, that is 2, and bending will be this 3 minus 2 is equal to 1. And for similarly, for ammonia molecule, NH3, N is equal to 4, and the fundamental vibrations will be 3 into 4 minus 6, that is 6. Stretching will be n minus 1, that is this 4 minus 1 is equal to 3, and bending will be 6 minus 3 is equal to 3. Although there are large number of fundamental vibrations may take place theoretically, but all transitions may not have the equally intensity. Even some transitions may not occur at all. So we should know the essential requirement for the IR absorption. What are the essential criteria to be molecule IR active? So it is called selection rule. Number 1, frequency of IR radiation should be equal to the frequency of vibrations. And number 2, for occurrence of strong transitions, there should have an appreciable change in dipole moment of the molecule during the absorption of energy. So, how and why change in dipole moment is essential for IR absorption? In IR, during vibration, dipole moment should be changed. Now consider a molecule containing A and B, and due to electronegativity difference, one atoms get positively charged and other gets negatively charged. Dipole moment is measured by mu. Now the atoms of the molecules may rotate. We know mu is equal to E into D, where E is equal to charge of atoms and D is equal to distance between the charge. Due to rotation or vibration, magnitude of the change does not change, but distance between the poles may change. This is suppose the in IR during vibration dipole moment should be changed. So this is from electromagnetic radiation. We know that electromagnetic radiation is consist of two components. One is electric component and other is magnetic component, and it interact with the molecules. The electric component of the electromagnetic rotation attracts the positive pole of the dipole. Hence, the position of the bending atoms are changed. Consequently, bond may be expanded. If vibrational frequency of the electromagnetic radiation matches with the vibrational frequency of the molecule, then molecule absorb electromagnetic radiation. Now, this is the way. Now, how it vibrate? Actually, the atoms of the molecule connecting the bond may stretch and compressed, stretch and compressed, and in this way vibration occurs. And when the electromagnetic radiation matches with the this vibrational frequency, then electromagnetic radiation will be absorbed. And this is the Morse diagram. Now, the types of vibrations. Two atoms connected to form the molecule. If atoms vibrate equally, the relative position of atoms change equally. Cartesian coordinates change equally, then it is called coupled vibration. We will discuss details in our next lecture about this matter. Today, I am only showing some snap. This is classical IR representation techniques, and another important, just I am touching the matter that Hooke's law vibrational frequency. We will discuss in next lecture details about this, and the dependence of vibrational frequency on various factors we will discuss in our next lecture. Today only saying the Hooke's law and vibrational frequency. The electromagnetic spectrum can be divided, as we have seen, into several regions differing in frequency of wavelength. The relation between the frequency and wavelength and the speed of light is given as E is equal to hc by lambda. And frequency in wave number is given by the equation nu bar is equal to 1 by 2 pi c root over k by mu in centimeter inverse, where k is equal to bond spring constant, mu is equal to reduced mass is equal to ma and mb by ma plus mb. C is equal to velocity of the light in centimeters per second, and we know that mu is reduced mass of AB bond system of masses, and m is the mass of the atoms, where ma is the mass of atom A and mb is mass of atom B. The isotope effect can also be calculated using the reduced mass and substituting the isotopic mass in the equation of the frequency in wave numbers. For example, HCl molecule, how can we calculate HCl molecule. What will be the mu? Mu is equal to mass of hydrogen and reduced mass of hydrogen, masses of hydrogen and masses of chlorine by mass of hydrogen plus mass of chlorine. In our next lecture, we will discuss details various factors of frequency, vibrational frequency dependence factors, and how it changes the IR of the various compounds. We will discuss details in our next lecture. Thank you very much for your patience hearing.